couple of examples of calculations with conditional probability and independence. So here's a tabular one. We sampled all the people in Littleton. There's an L in there. There we go. Littleton. All the households. There are 3,000 households total. And 2,000 of those households have kids. 1,000 do not. And we sampled and we asked them, how many TVs do you have? One or none was 1,800 out of the total. And two or more was 1,200 out of the total. And then here's the number for broken down into number of TVs versus number of kids. So calculations we could do, for example, would be the probability of having kids. That's just going to be 2,000 over 3,000. So that's 2/3. 2/3 of the households have kids. And then what about the probability that we have one or no TVs? That's going to be equal to 1,800 over 3,000. And that is 3/5 when you reduce it. Okay. Then what about, let's do some conditional probabilities. Conditional probability, what's the probability that you have, let's say, one or no TVs, given that, let's make that math mode for no good reason, given that you have kids. So remember what you do there. One way to do it, a good way to do it here, is that means we're only looking at this column, and that's our total right now. Out of the households that have kids, what's the probability? Okay, that's 1,000 over 2,000. So 1/2 of the households with kids have one or more TVs. So right off the bat, that tells us something interesting. That if you compare this probability to this one, it's less. That's less than 3/5. And so if I hadn't told you that a household had kids, you would have had to say, well, the likelihood is 3 out of 5, 60%, that the household you're talking to me about has one or no TVs. Yet if you tell me they have kids, that probably has gone down. So it makes it, so having kids makes it less likely to only have one or no TVs. Okay, so it should make it more likely to have more than one TV. Okay. Now, what about the probability? Like, let's look at an and. What's the probability of one or no TVs and, or in other words, intersection? I could write and, but it's just good to get used to the whole intersection terminology. Given that, or and having kids. Okay. So there's a couple ways to do that. Well, one is simply just those are the individual boxes in this diagram. One or no TVs and kids, that's 1,000 divided by the whole thing, 3,000, and that's 1/3. So if you don't tell me anything, just sample all the households, back to sampling all the households, what's the probability that these both will be true, one or no TVs and kids, 1/3? So that's one way directly from the numbers, but we should also be true that this is equal to, I'll just put it here, that should also be equal to, by our laws of conditional probabilities, that should be the probability that I have one or no TVs out of, I don't know why I insist on doing that, the probability of having kids times the probability of having kids. Let's check that. We calculated those numbers. The probability of having one or no TVs given kids is 1/2. And the probability of having kids in the first place in the household is 2 or 3. 2 out of 3. And indeed, that's 1/3. Okay. So either way you want to calculate it. This is probably more direct, given that I have all the information in front of me. But this is a little bit more conceptual. You kind of do it in stages. First of all, do I know how many kids households there are? Yeah, 2/3. Now, I've already calculated from among the kids' households which ones have one or no TVs, and you get the same number. So there's a lot more we could say about that, but I think that's enough for now. We could ask questions like, well, what about, look at 2 or more TVs, no kids. Look at these numbers, for example, real quick, and see if you can figure out, if I tell you the household has no kids, what's the conditional probability of having 2 or more TVs? And how does that compare? Excuse me, I'm still in my coughing mode. How does that compare to the probability of having 2 more TVs if I didn't tell you anything? Okay, so here's another problem. So in that problem, all the data was given, and so for example, we could do this problem with the AND just totally directly by counting, by looking at the entries in the table. And we didn't have to do it this way, but it was a good check for some of our laws of probabilities. But what about this one? Let's see. I have 2 pink balls and 2 green balls in an urn, just like, like a little jar. Okay. They always call them urns in probability problems. And here's what I can do. I'm going to pick 2 balls from the urn. And there's 2 very different ways I could do it. Suppose it was without replacement. No, suppose it was with replacement. That's easier and simpler. I pick one, and I put it back, and then I pick the other one. So let's see if we can think about, are the events first ball is pink and second ball is pink independent? Well, since it's with replacement, it's as if I didn't even pick that first one. Whatever I got on the first ball should not affect the second ball. And so that's a very important thing about with replacement. It really gives you that independence condition. Okay, so how can I use that? What's so good about that? Well, let's see. Let's calculate the probability that both balls are pink. Okay, that's always equal to. Oops. That's always equal to the probability that the second ball is pink given that the first ball is pink times the probability that the first ball is pink. That's always a law you can use. The probability of B is probability of B given A times probability of A. Very important law of probabilities. That's always true. And because they're independent, I don't need to tell you the first ball to calculate this conditional probability. That's just equal to, let's put it here, the probability, I'll just copy it and edit it. That's just equal to the probability, oh, I forgot to put this on 150%. It's a little bit late, but let's do it. In case this was not showing up on the video. Well, that's what I was doing before. Yeah, hopefully it shows up okay. And that means I definitely need to put this. Okay. There we go. Alright, that should be better. So now I was in the middle of editing this. So the probability that both balls are pink is just the product of the individual probabilities. First ball is pink, second ball is pink. Okay? And there's 2 pink balls and 2 green balls, so each time I pick, it's just a 1/2 probability of either one. So I get a very simple answer, just 1/2 times 1/2. Okay? So that's one way of doing that problem that kind of gets away from the raw counting idea and talks about if I know the probabilities for each individual piece, I can get the probability for something more complicated. And that's really great if you want to go further in probabilities. Okay, now what about without replacement? Are these events independent? Well, let's see. If I know the first ball is pink and I haven't put it back in, and then I ask, what's the is that going to affect the probability of the second ball being pink? Well, without that one pink ball, it's 2 green balls and 1 pink ball. So that's definitely going to affect it. So the answer is no. So does that mean we can't do any analog of this calculation? No, we certainly can, and it's actually sort of even more useful there. So the probability that both balls are pink, I can still use this exactly. Okay. And now, let's see. Well, let me do this part first. The probability the first ball was pink was 1/2. Okay. But what about the probability the second ball is pink given that the first ball is pink? Well, I just use the basic idea of conditional probability, which is, okay, let's just say the first ball was pink, and so I've picked a pink ball out. New situation. It's the probability that I pick a pink ball out of an urn with 2 green balls and 1 pink ball. So there's only 1 pink ball out of the 3, and so it's going to be 1/3. And so total, it's going to be 1/6. So this is something I want to highlight, is that conditional probabilities, even though they seem a little weird and seems like, oh, why do we have to learn this too? They're actually often pretty intuitive, because it just says, let's think of a new situation and calculate something that might not be that hard. It's just saying, if I change the situation to 1 pink ball and 2 green balls, can I calculate the probability of pink? Absolutely. And then I just multiply it by that first probability, and I get 1/6.